Okay, we have two strings, text1 and text2. We want to return the length of their longest common subsequence. If there's no common subsequence, return 0. Now, a subsequence of a string is a new string that you get from the original string with some characters from that original string or none of the characters deleted without changing the relative order of the remaining characters. So this is a subsequence of A, B, C, D, E, and we get this ACE by removing B and D from here. So we're looking for the longest common subsequence between any two strings. So subsequences generated from two strings, what's the longest common one? And these examples from Educative make it clear. So between found and cloud, OUD are subsequence that is common, are the longest subsequence, is the longest subsequence that is common between the two strings. And you get that by removing F and N and C and L in this case. In this case, ED is the longest common subsequence between these two strings, and we get that by removing B in this case, and R and A in this other case. And here there's nothing, so we return 0 because there's no common subsequence between them. This has there is no common string at all, right? Character between them. Hope that's clear. And so the key to this iterative approach, we've looked at the recursive approach prior, and most recursive solutions to dynamic programming problems require you to build like a visual, right, of the graph and how you're traversing it before you'd be able to internalize what it takes to write the code. So the diagram is more important to internalize. But in this case, we have a divide and conquer issue, right? It's like a classic divide and conquer problem where our goal is to divide the big problem into sub-problems and find a solution to the big problem by using the solution to the smaller problems. And so imagine we had these two strings, right? This one along the row here and this vertical string. And so sub-problems in this case, and in a lot of cases with the DP problems, is considering, okay, what if we didn't have this whole string? What if we had just one character? And we're looking for the longest common subsequence between this one character and all of this over here, one by one, right? Including like moving this one at a time. And so we set up a table like this and basically start, right? Evaluating things. And the zeros here mean, if there's nothing between, you have a string of length 0, then the longest common subsequence will be 0. So that's why we have these zeros here, and they're useful in building out the first solution. Because when we come over here, okay, assuming we only had G and G here, what's the longest common subsequence? They match, so it's going to be 1, right? 1, and it's going to be equal to 1 plus 0, actually, when you think about it, plus the 0 that is made when, okay, we weren't evaluating anything, right? So 0 solution is actually included in this first solution. And so we have 1 here because they match. And then we keep moving. But we pin this, right? We're keeping G here. And now we're evaluating A and G. So if A and G, we'd know that it's just 1, right? So we'd pick the max between what's on the right, this column on the right here, of assuming there was nothing here, which is bigger, what's here or what's beneath here, right? Which is the solution up until this point. And then we pick that. And then we keep going, doing that for every single thing here, just in this case of G, right? And we're going to get 1 because if there's only one character to compare, so the maximum is going to be 1 anyway. And then we keep moving, we'll move on to the next one. So for C, right, we're like, okay, if it was C and G, right, and just this one G, what's it going to be? What's the longest common subsequence? It's going to be 1, and we can get that from here, considering this subproblem of G that we've looked at before, and just bringing that in, right, between that and this subproblem over here of when there's nothing, right, and the maximum is 1, and that stays the same until we reach this C here, which means we're evaluating CG and everything that we've seen so far. And the table encodes that information for us, right, and brings it to us because in this case we add 1 plus, assuming these two C's weren't there, what was the best we've seen so far, which is 1 in this case. And that's what we do up until the end of the problem. That's literally how we get it done. Okay, so we reach the end. And then our answer is going to be this, right? What's what we end up having up here. Now, what does that look like in code? So we start out with text 1 and 2 in this function. We get their lengths, and we're going to use that to create this DP grid. 1 plus, right? Remember, we're using the empty string case, including the empty string case. Fill everything with zeros. So we're gonna get this grid, and then we loop through it, right? For every single row, right? We loop through every column for each row. And so whenever we see the same thing as we saw earlier, right, we have 1 plus the suffix that excludes those two things that row and column, if we think of them as cursors, are pointing to at that point in time, which is +1, right? +1, 1 after. So 1 plus whatever comes after for both of them. Otherwise, if they're different, right, we're looking for the biggest thing between, okay, if we don't include this particular character in text 1, which is represented by row +1, and if we don't include this character in text 2, which is column +1, and the bigger value between the two of them will be the longest, because we're looking for the longest, not the shortest. That's why we're using the maximum. We store that in dp grid, and then when we're done looping through every single thing here, we return dp grid of 0, 0. And now this solution that we see here can be built with prefixes instead of suffixes, so that instead of starting from the end, like you see here, we could start from the beginning and go out to the end. Okay, either way works. All right, and that's that about that. Just keep going till we get to the end. And this would be extremely tedious to do by hand, and that's why we have code, right? So yeah, hope that's clear. Again, you have to look at a lot of these problems so that you develop that intuition for knowing how to break things down in a whole divide and conquer, the spirit of divide and conquer, right? So using smaller problems to find a solution to the bigger problem. That is the gist of dynamic programming. And then if we look at the time complexity, we have m by n, which does make sense, right? Remember, n by m, the length, the text lengths, the various text lengths. And then space complexity as well, because we built that massive grid, right? It's going to be n by n as well. That's all there is to this problem. Thank you.